Hello everyone, this is Dr. Fan. Ramp question is a very popular topic in AP Physics, and today let's discuss the key issues for a block on a ramp. Alright, let's first use a MCQ to warm up. So the MCQ says a block is at rest on a ramp with an inclined angle of theta. Which one of the following statement is wrong? Alright, option A says the net external force on the block is 0. So based on Newton's second law, sigma F net equals to mass times acceleration, because the block is at rest, so the acceleration is 0, so the net force should be 0. So this statement is correct. And then it also says the friction force between the ramp and the block is static, which makes sense because gravity tries to pull the ramp down. So there is a tendency for the block to move down, but friction opposes this motion going up. Because the ramp and the block do not have real relative motion, only have a potential relative motion, so the friction force is static. So this is also correct. So option C says the static friction coefficient between the ramp and the block is equal to or larger than tangent theta. Clearly, this option requires us to do some calculation, and let's try to figure out the relationship between the angle and the static friction coefficient. Alright, so let me use a different color. For this question, what we can do is we can draw the free body diagram first. So we know there is gravity, we know there is a friction, we also know there is a normal force, right? And then we can construct a coordinate system if we use going down as my x direction and perpendicular to the ramp as my y direction. Then I can write down the Newton's second law along both directions. So for example, along x direction, my sigma fx equals to the horizontal component of my gravity, so this guy right here, Fg parallel to the ramp, and a vertical component of my Fg, so Fg perpendicular component. So how do I get these two components? If the angle here is theta, so this angle here and this angle here makes 90 degrees, and this angle here and this angle here also makes 90 degrees. So that means this angle here is theta. Then we can do the force decomposition. So because this is my horizontal component and this is my angle theta, so the horizontal component of gravity is mg sine theta. And friction is opposing the motion, so minus friction, and which equals to mass times acceleration. Because the acceleration is 0, so it equals to 0. You got to pay attention to this friction force here. It's static friction. We only know its range. We do not know its exact value yet. Now let's look at the vertical direction. So along the vertical direction, we have normal force, Fn, and we also have the vertical component of gravity, minus mg cosine theta, which also equals to 0 because the block is at rest. If I call this equation 1, this is equation 2. From equation 1, I know my friction force equals to mg sine theta. And from equation 2, I know my normal force equals to mg cosine theta. So remember, this is a static friction. We know the static friction force has a maximum value. So static friction force is smaller or equals to mu s, the static friction coefficient, times the normal force. So we know the static friction force and we know the normal force. We can plug all these values into this equation. Let's see what do we get. We get mg sine theta smaller or equals to mu s times mg cosine theta. Mg cancels out. If I divide cosine theta on both sides of the equation, I got sine theta over cosine theta smaller or equals to mu s. And I know sine theta over cosine theta is tangent theta. So that means in order for my block to be at rest on the ramp, I indeed need my static friction coefficient to be equal or larger than tangent theta. So this statement is also correct. So that means option D is wrong. That means the correct answer is D. So let's see what the D says. D says the kinetic friction coefficient between the ramp and the block is smaller than tangent theta. In order to know the kinetic friction coefficient, the block and the ramp needs to have relative motion, but that's not the case in this question. So option D is wrong. So we have solved this question, but I want to mention one thing that we learned from this question. From this question, you guys can see that there is a horizontal component from gravity pulling the block down, which is mg sine theta. And the static friction force can oppose that motion. And the maximum static friction force can be as large as this guy, so which is mu s times mg times cosine theta. So in this case, our mg sine theta is smaller than the maximum static friction force, so the block is at rest. What if mg sine theta is larger than mu s times mg cosine theta? Then the block is gonna go down. So what can we learn from here? If we do this simplification, if we divide the cosine theta on both sides of the equation, in this case, it's gonna be sine theta over cosine theta, because mg cancels out, is larger than mu s, which is tangent theta. So that means when tangent theta is larger than the static friction coefficient, then the block will go down. So let's see, block will move. So why this is important? Because it tells us the relationship of the angle and the static friction coefficient. And you can use this method for experimental design questions. For example, if the question asks you to determine the static friction coefficient of a certain surface, what can you do? You can change the incline angle of the surface. For example, this is your incline angle, theta, and then you can gradually increase this angle until at a certain angle. For example, when theta equals to 45 degrees, your block just starts to move. That means your mu s equals to tangent 45 degrees. That means your static friction coefficient equals to 1. So you can use this relationship to determine the static friction coefficient of a certain surface. Alright, now let's look at another question. So this question says a block is released from the top of the left ramp, so released from here, then smoothly transitions onto a frictionless level ground, so transitions into this level ground here, and then it climbs up the ramp on the right. It also says the incline angle for both ramps is 45 degrees, so this is 45, this is 45. And the kinetic friction coefficient between the ramps and the block are the same, so 0.2. So we know the kinetic friction coefficient here and here. The question also said the length of the left ramp is 1.2 meter, so the total length from here to here is 1.2. And the question asks, what is the furthest distance the block will reach on the right ramp? In other words, how far the block is going to climb on the right ramp. So because it's asking the distance, so clearly it is related to kinematics. So let's review the motion. So because the block is released here, so the initial velocity is 0. Then because it's moving down, we know it's accelerating. So when the block goes here, it's going to have a certain velocity. Let's call it v1. And because on this level ground, it is specifically mentioned it's a frictionless level ground. So that means horizontally there is no resistance, so the velocity would not change on the level ground. That means the velocity is still v1 here, right? And then eventually the block is going to continue to move until its velocity become 0 again. And that is the moment the block has the furthest distance on the right ramp. So this is the motion. So how do we actually solve this question? So because it's a kinematic questions, we need to think about parameters like velocity, acceleration, and displacement. So the displacement is given here, and we know the velocity relationship. So maybe we can find out the acceleration. So how do we find out the acceleration? Then we can draw the free body diagram and use Newton's second law. Let's first consider the motion of the block on the left ramp. So the block is under gravity here, we know that, and there's a normal force, and there's a friction. And because it's moving, so it's kinetic friction. So let me put it here. I'm gonna use the same coordinate system. So this is my x going down, this is my y perpendicular to the ramp, right? And remember, this angle is theta. We discussed that already. So now let me write down the forces along x direction. So sigma fx equals to mg sine theta, which is the component of gravity along the ramp, minus the kinetic friction force, which equals to mass times acceleration. In this case, we have acceleration because the block is going down. And along the vertical direction, we have normal force again, and we have another component from gravity, which is mg cosine theta. Because there is no motion along the vertical direction, so it's 0. So let's label this as 1 and 2. And then from equation 2, we know the normal force is mg cosine theta. And because this is kinetic friction, so we can find the kinetic friction directly from my normal force. So my kinetic friction force equals to mu k times my normal force, which is mu mg cosine theta, which is mu k, kinetic friction. So then I can substitute this value into equation 1, then I can get my acceleration. Let's see how it looks like. So it's going to be mg sine theta minus mu k mg cosine theta equals to m times a. So that's my acceleration. So then my acceleration is going to be, all the m cancels out. So it's going to be equals to g times sine theta minus mu k g cosine theta. All right, so now I know my acceleration. I also know the length. So I can find my final velocity here using one of the kinematic equation. Remember, there is one equation which is v squared equals to v0 squared plus 2a delta x. This is one of the kinematic equation, right? So for this case, my initial velocity is 0, so it's 0 squared plus 2 times my acceleration. Acceleration is positive because it's going down, times the length. Length is also positive because it's going down, equals to v1 squared. So that's my velocity here. And then if I substitute all this value in, so my v1 squared equals to 2 times my acceleration, g times sine theta minus mu kg cosine theta times L. So I know my final velocity here. Of course, I have all these values, I can solve it. But in this question, you don't need to solve it. I'm going to show you guys later. All right, so now let me change to a different color. So I know my block's velocity do not change on this frictionless level ground. So I know the velocity here when the block enters or climbs the right ramp is going to have the same velocity as v1 here. So the velocity here is v1 too. And the final velocity when it climbs the furthest, the velocity is 0. So as long as I find the acceleration during this motion, I can find the length. So how do I find the acceleration? Again, do the free body diagram. So if I write down the gravity going down, normal force, perpendicular, and in this case, the friction is going down. because the block is moving up, so the friction is going down. So you have kinetic friction here going down. So now I set this as my positive x, and this is my y. And I can do a Newton's second law again. So if I look at along the horizontal direction, sigma fx equals to, I have a kinetic friction force here. I also have a component from gravity. So I got ff, in this case, is plus mg times sine theta, right? And that equals to mass times acceleration. And along the y direction, I got Fn minus the vertical component of gravity, mg cosine theta, which equals to 0, because there's no motion along the vertical direction. So similarly, you can see that my normal force does not change, which is mg cosine theta, which means my friction force does not change. So my friction force, which is kinetic friction, equals to mu k times mg cosine theta. But my acceleration does change. Why? Because let's plug this value in. Let's see what do we get. So this is my friction force, mu k mg cosine theta plus mg sine theta, which equals to mass times acceleration. Let me call it a prime. So then my acceleration is what? My acceleration is g times sine theta plus mu kg cosine theta. So you can see that here for the acceleration on the left, there is a minus sign, but here for the acceleration on the right, there is a plus sign, which makes sense because while the block is moving up on the right ramp, both gravity and friction force is opposing this motion, right? Okay, now if we know the acceleration, we can use the kinematic equation again. Let me clean this area. All right, so I'm gonna write down the kinematic equation. Remember, my positive x is going down. So that means my initial velocity is minus v1 squared, right? My final velocity is 0, so it's 0 squared. Now plus, remember, 2a delta x. So it's 2, then is this acceleration here, right? So it's g times sine theta plus mu kg cosine theta. And because my displacement is going up, but my positive direction is going down, so this should be minus L prime, right? So if I simplify this, what do I get? I get v1 squared equals to 2 times g sine theta plus mu kg cosine theta times L prime. So this is a maximum length I'm gonna reach, right? All right, so let me do the final step here. So because this velocity here and this velocity here are the same, so I can equalize them. So then I can simplify this equation because I can get my L prime right away. So let me see, what do I get? So my L prime equals to this whole thing, right? 2 times g sine theta minus mu kg cosine theta times L, and divided by this whole thing here, divided by 2 times g sine theta plus mu kg cosine theta, right? All right, I do know my mu k. I do know my angle here, right? 45. In this case, if you plug into all the values, the answer you get is gonna be 0.8 meter. Okay, this is a pretty complicated question because it involves both dynamics and kinematics. But this is a very good practice because it not only involves dynamics and kinematics, but also involves friction, and the friction can change direction. If you understand this question, you should have a very good understanding about questions related to ramp. All right, now let's summarize what we have learned. So How should we solve questions related to ramp? The first thing is to determine the motion of the block, right? Whether the block is at rest or the block is moving, which is very important. Whether it has friction or it does not. The second thing is draw the free body diagram. You always have gravity going down and normal force perpendicular to the ramp. You may have friction this way, you may have friction this way. It depends on the situation. After you draw the free body diagram, Newton's second law can help you. You construct a coordinate system along the ramp and perpendicular to the ramp. Then you do force decomposition. From this Newton's second law, you can find out forces and you can find out acceleration. And if they ask you questions about kinematics, you can combine acceleration with kinematic equations to solve either time, displacement, or velocity, which is the last question we just addressed. Hopefully this video helped you to understand the block on the ramp question a lot better. Thank you. I will see you next time.